Alright, so we're starting here with Precal, and we're starting with section 1.2, and it's functions and graphs. You can look back at section 1.1 in your book when you get your book. If there's any questions, you can ask about them, but that stuff is such a review. It should be stuff that you should be very comfortable with. If it's not, that's fine, and ask questions about it, but I'm not going to cover that and make that something that you have to do. All right, now a relation, this is review as well, but this is very important and you need to make sure that you get it. A relation is any set of ordered pairs. The set of all first components of the ordered pair is called the domain of that relation, and the set of all second components is called the range of the relation. Now, another way that you will hear these referred to is that the independent variable is called the domain, and the dependent variable is called the range. And that's different applications for it. Essentially, they're the same, but it's just different, defined a little differently, and use different words for kind of just touch of a different meaning. All right, so find the domain and range of the relation. The relation we have is Smith is 1.006%, Johnson is 0.810%, Williams 0.699%, Brown 0.621%, Jones also 0.621%. So when we go to list these, the domain, and this is how you list this because these are elements of a set, and when we say the domain, it is the set of elements that are the first components of these ordered pairs. So the domain would be Smith, Johnson, Williams, Brown, and Jones. And then you would close your set with a pointy bracket things. I can't draw those worth of crap, so you just go ahead and have to deal with it. It gets worse every time I try to improve it. So anyway, there's the domain. It's the set of the first elements of each ordered pair. The range is the set, so we get the pointy brackets again, of all the second elements. Now, you only have to list them, all the ones that occur. If something repeats, you don't have to list it twice. So in this case down here, I'm not going to have to write 0.621% twice. So you got 1.006% and 0.810% and 0.699% and 0.621%, and then that's all of it. Because right there with those four numbers, we've listed every second element here. Every second element that occurs in any of those ordered pairs. All right, now, a relation is one thing. It's a set of ordered pairs. A function is a special relation. Okay, a function is a relation in which no two ordered pairs have the same first component. That's one way of thinking about it. That's one way. If you look through a list and you don't see any that have the same first component, then you're good as far as it being a function. Now, the more mathematical definition, a function is a correspondence from a first set, the domain, to a second set called the range, we've already talked about those, such that each element in the domain corresponds to exactly one element in the range. Another way to simplify this out is to say this: for any x value, there is only going to be one y value that goes along with that x. So if your domain or your x value is 4, and you have one point that's 4, 2, you cannot have any other point that has 4 as an x value with any value other than 2 as a y value. So a function can have two different first components with the same second component, but it can't have two first components that are the same with two second components that are different. All right, so determine whether each one of these is a function. So as we look at this one, we've got 1, 6, 2, 6, 3, 8, 4, 9. So do we have any repeating first components? Well, we've got 1, 2, 3, and 4 in our domain. We have 4 different elements for the ordered pairs. Therefore, we know that we are not going to have two y values for one given x value because x does not repeat. So this one is a function. So yes. All right, looking over here at this one, well, we're good here with the 8, 3 and the 9, 4, but the 6, 1 and the 6, 2, for a given x value of 6, we have two different y values that are going to go along with it. So that right there makes it not a function. So like we said in this last step down here, we can have two components or two different first components with the same second component here and here, but we cannot have two second components that have the same first component. Here we have two y values for a given value of x. Here we have two y values for different value, or one y value for different values of x. Now, determining whether an equation represents a function, what you're going to do is you're going to solve for your y, and you're going to determine whether or not there's a plus or minus. Now, I'll show you a little more once we work into this, but determine whether each function defines y as a function of x. So if we solve this thing right here for y, all we're going to do is we're going to move the x squared over. So y equals negative x squared plus 4. So what we're asking, is there a way that I can get two different y values when I plug an x value in? So let's say we plug in 1 right here. Is there any possible way that I can get two y values? Well, there is no way. So that's what we're looking for. Is it possible to get two y values for any given x value? In this case, it's not. So yes, this is a function. Now, over here, it's a little different. We're going to move that x squared over. So we're going to get y squared is equal to, I'm going to write this just a little bit differently than this, 4 minus x squared. Now, I haven't solved for y. I've solved for y squared, but I need to solve for y. So I'm going to end up taking the square root. So that's going to give me y is equal to, and when I take the square root of this, remember, if you're looking for every possible solution with a square root, there's a plus or minus. And 4 minus x squared. Now, you're probably wondering, well, why in the world is there a plus or minus? Well, here's the thing. If you take the square root of 4, everybody's going to say that that answer is 2. Well, the thing is, that answer can also be negative 2. Because remember, what are we looking for, and what does it mean when we take a square root? We're looking for all the numbers that when we multiply those numbers times themselves, we're going to get this number in the middle. 2 times itself gives you 4. Negative 2 times negative 2 gives you 4. Both positive. So that's why we end up with a plus or minus. Now, look at this. For a given value of x, let's say we're going to do x is 0. Let's just say x is 0. If x is 0, we're going to have plus or minus the square root of 4 minus 0, which is going to be plus or minus the square root of 4, which is equal to plus or minus 2. Well, remember, when we're looking at that, that literally means positive 2 and negative 2. It's two different answers. Don't look at this and think of it as one number. It's two numbers. It's a positive 2 and a negative 2. So right there we know that this function, or this relation, is not a function because for any given x, for one x value that I plugged in, I can get two values of y. So this is a big no. And that is typically when you're going to have a function that's not, or sorry, a relation that's not a function, when you end up with a y squared, that you have to take a square root to solve for y. All right, now to evaluate a function, all we're going to do is plug it in. Function notation is what we're dealing with right here, and it says f of x, if f of x is x squared plus 3x plus 5, evaluate each of the following. Now remember that when we have function notation like this, if f of x equals x squared plus 3x plus 5, then f of 2 is just putting a 2 anywhere I had an x in this expression. So it's going to be 2 squared plus 3 times 2 plus 5. And then, of course, we can simplify. And we're going to have 4 plus 6 plus 5, so that gives me 15. So the answer to A is 15. Now, for B, it's a little bit different, but it's the same idea. F of x plus 3, we're just going to put x plus 3 everywhere there was an x in the original one. So I'm going to have x plus 3 squared plus 3 times x plus 3 plus 5. And then all I have to do is square this, multiply, distribute it here, and simplify and get everything like it is. Now remember, with the x plus 3 squared, you have to FOIL it out, unless you remember the shortcut, and the shortcut is not x squared plus 9. That is not correct. The shortcut is to square the first one, multiply these two together and double it, so plus 6x, and then square the last one. Alright, distributing, of course, I'm just going to get plus 3x plus 9, and then my plus 5 is just kind of tagging along. So now simplifying down, I got x squared, nothing else to combine with it. 6x plus 3x gives me 9x. And then 9 plus 9 is 18, plus 5 gives me plus 23. All right, now for the last one here, we've got f of negative x. We can write it right over here. And what that means is that we're actually going to take and put in a negative x, the same way we did everything over here. We're going to put a negative x in everywhere we have an x up here. So I have negative x, quantity squared, plus 3 times negative x, plus 5. Let me change colors here so they don't all run together. All right, and then when we go to simplify, what's going to happen? Well, we have negative x squared. Anytime you square a negative, you end up with a positive. So we end up with positive x squared. 3x times a negative x gives me negative 3x, and then plus 5. So there is f of negative x. Now, if you remember, and if you don't, that's okay. We're going to talk about it a little later anyway. That is a way to determine whether or not a function is even or odd by plugging in a negative x. But like I said, if you don't remember that, we'll talk about it later. All right, now, graphs of functions are going to, let's graph the function f of x equals 2x and g of x is 2x plus 4 in the same rectangular coordinate system. and we're going to select integers only for x, starting with -2 and ending with 2. All right, so we're going to start off with an ordered pair, or actually we're going to start off with a t-chart. We're going to go ahead and get all our points, and then we'll just put it into a graph that we'll draw over here. So here's my x, and I'll put f of x here, and I'll put g of x here. Remember, f of x is 2x, g of x is 2x plus 4. And they say start with -2 and end with +2. So -2, -1, 0, 1, and 2. So if we have -2 and we double it, we're going to get -4. -1 double it, we're going to get -2. 0 doubled, we're going to get 0. We get 2, and we're going to get 4. Now when we take those same numbers, remember this, notice what's happening here. We're just taking this thing right here and we're adding 4 to it. So every one of these numbers, if I just add 4 to it, I'm going to get my g of x. Now if you think about this, what does that do? That takes every point that I have here and it just shifts it up 4 units. It's a vertical shift of this line. This is going to be a line. This is just a vertical shift of that same line. So -4 plus 4 gives you 0. -2 plus 4 gives you 2. 0 plus 4 gives you 4. 2 plus 4 gives you 6. And 4 plus 4 gives you 8. Alright, so let's kind of sketch this graph out a little bit. Now, before we go too far, let me go ahead and do this. We'll make that green. Do this. And we'll make that red. So that's where our points are going to come from and what color we're going to do. So let's do the 2x first, or the f of x. So we've got -2, 1, 2, and 1, 2. That's as far as I'm going to go. And we got 1, 2, 3, 4. 1, 2, 3, 4. Now we're going to need more than that, but we'll just go with it when we get there. All right, so -2, -4. That point right there. -1, -2. That point right there. Remember, the first one is your x, side to side. Second one is your y, up and down. And then 0, 0 at the origin. And then 1, 2. And 2, 4. So there's my line right there. Close enough, anyway. All right, so when I go back and do this one, remember, for each one of these points, it just shifts up 4 units. We're going to see that as we start adding our points in here. So when x is -2, instead of being at -4, I'm at 0. So -2, 0. -1, 2. 0, 4. 1, 6. So there's 4, 5, 6. And then 2, 8. So at 2, I'm going to go up 4 and go 5, 6, 7, 8. And then there is that line. And I didn't do too bad because they're supposed to be parallel, and look at there, they kind of look parallel somewhat somehow. So all that +4 right there did was create a vertical shift for every point. Notice it doesn't look like the lines are 4 units away from each other, because if you draw from here to there, they're not. But this point right here moved up 4 points. This one moved up 4 units. This one moved up 4 units. This one moved up 4 units. But the perpendicular distance between them is not going to be 4 units. All right, now if any vertical line intersects a graph in more than one point, then the graph does not define y as a function of x. For instance, hang on here. If I take and I draw a vertical line, and I move that vertical line, let me get it vertical first, there we go, and then I move that thing across, right here I'm good. But as soon as I get to here, notice that the green line hits two places, right there and right there, and that means that this thing, this blue line here, this relation, is not a function. Now if we continue on, it becomes very obvious. Right there it's hitting three places. Still three, there it's two. But it only has to do that one time on the domain of the relation, and that makes it not a function. So if we use the vertical line test, are each of these, determine whether or not each of these is a function or not. Well, right there, no. This one, if I slide a vertical line across, it's only going to hit one time everywhere, so yes. This one, same thing. It's going to hit one time and one time only, no matter where I draw a vertical line in there, so that's a yes. This one, it doesn't hit it all over here, but as soon as I draw one line over here, and imagine that's vertical and straight. I know that's a lot of imagination there, because I can't draw a vertical or straight line. I definitely can't draw both of them. So that one is going to violate the vertical line test, and therefore that is not going to be a function. Now, you can obtain information about a function from its graph. At the right or left of a graph, you will find closed dots, open dots, or arrows. A closed dot indicates that the graph does not exist beyond this point, does not extend beyond this point, and that last point does belong to the graph. That's called a closed interval, or at least the closed end of an interval. That's why it's a closed dot. An open dot indicates that the graph does not extend beyond that point, or it's missing a point, and the point does not belong to the graph. That means it's a hole in the graph, or that last endpoint is not included in the values of the graph. And of course, we know this from years and years and years of studying. An arrow indicates that the graph extends indefinitely in the direction that the arrow points. Now, don't worry about looking at example 7 on page 155 unless you just want to, but you can look at graphs and you can get a lot of information. This is the time after infection on this axis, and this is the average T cell count per milliliter of blood, and this tells you exactly what's happening over the 11 years, and you can also make note of certain things that happen along those ways. So you can get, graphs are really useful for showing a lot of information at one time, and to see trends that may be developing, behavior that's happening over time, and things like that. Graphs can be very, very, very important, and being able to read them is important as well. Now, domain and range, we talked about at the very beginning with relation. Domain was the first part of the input, of the ordered pair, and range was the second one. Well, when we're talking about a relation in a graph, the domain is the set of inputs. It's the values that we're putting into the function, and then the range is the set of values that are coming out of the function with those inputs. So it's also known, as I said before, the domain is the dependent variables. They're independent variables because you can choose anything you want to. The range is the dependent variables because they're dependent on the values that you choose. The range values are dependent on what values of the domain you use or choose. Now, so when we're looking at a graph, the domain is all the x values that are included. When you look at that, you say, what's the smallest x value that's included on my graph? In this case, it will be whatever this value is. What's the largest domain value, or the largest x value? Well, it's this one over here because we've got those closed endpoints. This is called a closed interval. Both endpoints are closed, and that's a very narrow domain. It doesn't include all real numbers. And then the range, you're just asking the same thing you asked about the x's, but about the y's. What's the smallest y value in this graph? Well, it's going to occur right there. And what's the largest y value in the graph? Well, it's going to occur at the top part here. It's not right there at that point, because it has values right here that are above that point. All right, so when we're looking at this function right here, it's a semicircle. What is the domain? Well, the domain are all the x values. What's the smallest x value? Smallest x value is -4. What's the largest x value in this graph? Well, it's 2. So our domain goes from -4 to +2. And the range is going to go from 1 all the way up to 4. 4 is the largest value there. Now, there are a couple of different ways you're going to see this thing. You need to know how to read set builder notation. It's not going to be something that I'm going to require you to do. Interval notation, definitely you're going to have to know what to do. But reading set builder notation, I want you to know how to read it, just so that you actually know, if you see it somewhere, you'll be able to decipher what it means. What this says is, this is talking about the range, by the way, and it says the range is all values of y such that, that's what that vertical bar is for, y is between +1 and +4. That's the way you'd read it. You could also read it like these blue boxes down here. I like the way I read it better. Now, interval notation is a lot simpler. All you're going to do is, if it's got a closed dot over there, you're going to have a bracket. If this had been an open dot, that would be a parentheses. So an open dot, so if it's open, you're going to use parentheses. Closed, you're going to use brackets, and that occurs with either end. So let's say, for instance, let's change colors here, and let's say that I actually made this an open dot. Well, how would I write that interval now? Well, if I'm talking about the range, it's still including 1 over here, so it doesn't change. I may not include 1 here, but I am including 1 there, so it is included in the values. Now, what about when I talk about the domain? Well, the domain is going to be -4 to 2. Am I including the x value of -4? Well, with this open dot, no, I'm not. That's where the parentheses comes in. When I get over here to +2, am I including the 2 in my domain? Yes, I am, so I'm going to put a bracket. So that would be the domain. And that's called a mixed interval, where both ends are not both open or both closed. This is a mixed interval. And in this case, we're looking at the interval notation for the range, and notice that both ends are closed. It's including 1 and it's including 4. Even though there's not a closed dot up here, remember, you are actually getting up to 4 as a y value and then coming back down. All right, use the graph of each one of these functions shown to identify its domain and its range. So looking at this one, I want to find the domain, I want to find the range. I'm going to use interval notation. What's the smallest x value that I have here? -2. What's the largest x value that I have here? 1, closed dot or open dot, closed dot, so a bracket, closed dot, so a bracket. And what about the range? What's my smallest y value? 0. What's my largest y value? 3. Once again, closed dots on either end means we're including those endpoints. So closed brackets. So the brackets are included. All right, same thing over here. Let's look at the domain. We're going to look at the range. What's the smallest x value that I have on my graph? Well, it's -3. Am I including -3? Well, no, it's got an open dot, so that's where I put parentheses. What's my largest value of x? It's 2. Okay, is 2 included in my domain? In other words, is it part of my graph? Yes, it is. So I put a bracket there. So there's my mixed interval. All right, what about my range? Smallest value is 1. Largest value is 2, so it doesn't go very far. And what do we know about 1? Is it open or closed? Well, right there, it doesn't actually have the value of 1, so it's going to be parentheses. And here it does have the value of 2, so it's brackets. All right, what about this one? Well, domain, range, domain, what's the smallest x value we have defined, or part of the graph? So it's -2. And the largest one is +1. Is -2 part of our graph? Yes, it is, so we've got a bracket. Is 1 part of our graph? No, it's not, so we've got a parentheses. All right, what about the range? The range, what's the smallest y value we have? Well, it's 1 right here. What's the largest y value we have? Well, it's 5 up there. What do I know about the 1? Is it included in the graph? Yes, it is, so I got a bracket. What about the 5? It's also included in the graph, so I've got a bracket. All right, so with this one, we're not going to write them out, but we'll just talk about them. What do we know the domain is here? And you can practice writing them in interval notation, and then I'll show you what the answer is so you're not sitting here watching me write again. So in this one, what's the smallest x value you're going to have? Well, it's going to go forever in this direction, so it's going to be -infinity. Negative infinity is not really a number, so it can never actually include that number. So infinity or negative infinity will always be a parentheses. It's never going to be a bracket. And then what's the largest x value that you're going to have here? Well, it's going to occur at 4. All right, and then your domain, that's your domain, so what about your range? Smallest y value, 0. Largest y value, this is going to grow. It's going to grow kind of slow, but it's going to continue to go on and on and on and on up, so it's going to infinity. So here's what your answers would look like in interval notation. Domain from -infinity to 4, range from 0 to infinity. All right, now this one is going to be a little weird. Now, as far as the domain, what do we know about the domain? I'm not going to write them out right just yet, but I want to go ahead and get this part written down. What do we know about the domain? Well, it starts, our lowest x value is at, all right, so for this one, the domain, we pick up an x value at 1, and we have an x value for every single value of x, all the way up to but not including 4. So we have a value from 1 to 4, including 1, not including 4. Now, when we get to the range is where it gets a little difficult and a little weird. What do we notice? Well, from 1 to 2, not including 2, we have a value of 1, a y value that's 1. And when we get from 2 to 3, not including 3, we get a value of 2, and so on and so forth. So instead of an interval like this, we're kind of flashing back to what we were dealing with just a second ago where we were listing a set. what is the set? Well, it's either going to have a value of 1, a value of 2, or a value of 3 for all values from 1 to 4. The range is only 3 elements. It's either the value of 1, the value of 2, or the value of 3. All right, intercepts are where a function or a relation is going to intercept the axis. Now, when we're talking about a function, these things are true. For a function, you're going to have one and only one y-intercept. A function can have more than one x-intercept, but at most, it's going to have one y-intercept. Now, what we'll end up, we'll talk about how to find these and all that, but we can have multiple x-intercepts, but we're only going to have one y-intercept if it's a function. Because if it has more than one y-intercept, then it violates the rules of a function and has two y values for one given x. All right, so that's where we're going to stop with this